Welcome back to Dave Does Math from Home. This is part 2 of our video about continuity, and in this version we're going to be talking about continuity analytically, or how to find continuity analytically without any graphs involved, just using the equation or the formula of a function. For this, we're going to just start with a function. Let's say f of x equals, we'll do x squared minus 2x minus 15 over x squared minus 9. This seems like a good one. So, when we evaluate the continuity of something like this analytically, we need to, it's going to be wrapped up very closely in limits and how we're going to deal with the limits here. So I think we can probably see right away that whatever else is going on here, the bottom is going to factor into x plus 3 and x minus 3, which means that we're going to have problems, domain restrictions, at x equals 3 and x equals negative 3. And that's probably where we should be considering the continuity of this function when we have domain restrictions. We already said that polynomials mean no weird stuff, and no weird stuff includes they're always smooth and continuous. So if you just have a polynomial, it's continuous everywhere. You don't have to do any work. Sine, cosine, those are continuous everywhere. You don't have to do any work. Exponentials are continuous everywhere, no work required. Logarithmic functions are continuous everywhere on their domain, so they have those vertical asymptotes, and as long as you stay away from the vertical asymptote, you'll have continuity. But they do have some domain restrictions, so they're obviously not continuous when they don't exist. But as long as the function exists, as long as a logarithmic function exists, it is continuous at those points. So these discontinuities are going to come from things like zeros in the denominator. So let's explore these. I want the limit as x approaches, let's start with 3. The limit as x approaches 3 of f of x. So like I said, we're going to explore this continuity by talking about the limits. From our definition of continuity that we saw in the last video, we know that a function is continuous if the function exists and the limit exists and they agree. So this idea of continuity is very tied up in the idea of limits. And the good news is it's so tied up in the idea of limits that we can pretty much just do the limit and use that result to determine the continuity. Which comes back to something I said about limits in the video for section 2.3, I think, or 2.4 maybe. I said that every single time we do a limit, we need to start with plan A. Even if you know how it factors or how it simplifies, if you're doing that early, you still have to start with plan A and plug your numbers into the original function, because the results of plan A are going to give us very useful information about continuity. And we'll see what I mean by that. And actually, let's see what I mean by that right now. Let's start by exploring the limit as x approaches. We'll go with 0. When x equals 0, if I want the limit, I'm going to do this with plan A. Plan A means I'm not going to do anything with a simplified or factored or easier version of this. I'm always going to use the original for plan A. And this is going to turn into 0 minus 2 times 0 minus 15 over 0 squared minus 9. Looks like 15 ninths probably simplifies down into 5/3. Okay. Because plan A is giving me a number, plan A giving me a number means that the function is defined at this point. F of 0 is 5/3. Because plan A is basically just evaluate f of 0. That's what plan A means. You plug the number in, you get 5/3. 5/3 is f of 0. And this means that the function value exists, the limit exists, and they match. Anytime plan A succeeds, that means that the function is continuous. This is a badly drawn view. Plan A means the function is continuous every time. Let's look at a different point here. Let's look at x approaches -3. I'm still going to try plan A. I'm always going to start with plan A because whether or not plan A succeeds tells me about the continuity. If you skip plan A and simplify this and go straight to plan B, you'll get a limit, but you won't know whether or not the function is continuous or something else. If plan A fails and you have to go to plan B, then you know it's not continuous. Plan A only fails when f of that number doesn't exist. If the function value doesn't exist, then plan A is going to fail. That's what kicks you into plan B, and that tells you about the continuity. So don't skip plan A. Plan A, when I plug in -3, is going to be, well, I already know it's going to fail. So let's see how badly it fails. 9 plus 6 minus 15 should be 0. 9 minus 9 is 0. Okay. That's kind of a catastrophic failure. So plan A didn't work. Now we can start simplifying this and we'll see what plan B looks like. I think the top is going to factor into x plus 3 and x minus 5. Looks like. So these guys will cancel as long as x does not equal -3. Good news, I'm taking a limit, so it doesn't actually equal -3, we're just pretending it does, which is completely different and totally safe. So when I hit this guy with a plan B, it's going to look like, I'm going to plug this number into the simplified version, so I think I should get -8 over -6, which is 4/3 when that simplifies. So, I have a limit from plan B, and here's what this means. Anytime plan B is the plan that succeeds, that means that the function does not exist, but the limit does. As long as the limit exists, that means it looks like it's going to a point, it just doesn't actually quite get there. That means it's fixable, removable. This is a removable discontinuity, which is always what plan B means. When plan A succeeds, you have a continuous function. When plan B succeeds, you have a removable discontinuity. All the time, every time. As long as you can get a limit, you can fix the function by changing that one value to this, and then you have a continuous function. There's one more case. Let's look at the limit as x approaches +3. Again, we're going to start with plan A because we always start with plan A. That will give us 9 minus 6 minus 15 is probably -12. Oh, sorry, f of x. -12 on top. The bottom is still going to be a 0. Plan A has failed us. So, now that we know it's not continuous, we can move to plan B. We've already got the simplified version. We're going to plug it into this guy. That will give us, plan B is going to look like -2 over 0, which also is not going to work for us. That is the double failure. So now we hit plan C. Plan C means the limit does not exist. If the limit does not exist, that means the function doesn't look like it's doing anything. or it looks like it's doing two different things, which means you can't fix that. This is a non-removable discontinuity. Because this is an asymptote. If you think back to what we learned about rational functions, this is a little hole in the graph. The domain restriction you get from canceling factors gives you a little hole in the graph. That's removable. The stuff that stays in the denominator gives you vertical asymptotes. That is non-removable. And that's basically all there is to it. The reason that we have these limits structured in terms of plan A, plan B, plan C is so that as you go through this process and find your limit values, you are also very clearly establishing the sort of continuity status. Plan A always means continuous, because plan A is just plugging a number into a function. If you evaluate the limit by evaluating the function, then of course they're going to match. You have continuity. If you have to change something in order to evaluate the limit, but then you still get a limit, that means that the function doesn't exist at that point, but the limit does. That's removable. And if you cannot fix anything and the limit does not exist, then you cannot make that continuous. That's pretty much the whole section. And this concludes chapter 2. After this, prepare yourselves for an extremely exciting test about limits. And then when we're done with that, we will start chapter 3. We'll do some real-life calculus now that we know about limits. It'll be a good time.